But if one of the recordings is lost, it pretty much say the same thing, morning and the afternoon. So Monday and Wednesdays are typical lab days, and actually I have a morning class that meets right before this class. And so if you miss a lab, it gives you an opportunity to make up a particular lab. You can come in extra morning or something, make up the work. We can do that for most labs. Some labs we can't because of the equipment constraints, but otherwise, try to make up any labs that are missed. We'll talk more about that in a minute. But we're jumping to chapter 24. We're going to cover the first 3 sections, and then we're going to come back down to chapter 13. So chapter 13 is kind of where 1A left off. Actually, 1A left off with chapter 14. So in 1A, we jump from 12 to 14, skip 13. So now we're coming back to 13. We're going to do 13. Chapter 13 is thermodynamics part 2. So we're going to be looking at energetics one more time. Cover that. And then we're going to chapter 15. Chapter 15 starts a long series of chapters all devoted to equilibrium, chemical equilibrium. And chapters 15, 16, 17, and 18 have very similar equilibrium calculations. So we're going to spend a lot of time working equilibrium calculations and understanding these equilibrium systems. So that's 15 is our start. And then *16 is equilibrium applied to acid-base systems. 17, acid-base systems again. 18 to what we call solubility, precipitates, that kind of stuff, and complexes. So 15, 16, 17, and 18 are 4 chapters of equilibrium. And then we go to chapter 19, which is electrochemistry, and then to chapter 20. Chapter 20 used to be the old chapter 13 in the 10th edition, but it's chemical kinetics, the speed of reactions. Okay, from chapter 20, we'll go back and finish chapter 24, the rest of the sections. And so I just call it part 2, transition metal complexes. And then we'll finish the semester with chapter 25, which is nuclear chemistry here. The final exam is going to be comprehensive. The final exam is going to be split over 2 days. The first day, which is the lab day, this will be a 3-hour block, and that's going to be multiple choice. And then the second part of the final will be on the lecture day, which is an hour and a half or so, a little less, and that'll be like free response questions. And both of them will be comprehensive. They'll cover all the material from the beginning to the end. That's the final. What about midterms here? When's your first midterm? And actually, I don't have the midterm dates there because it depends on how well I stick to the schedule. Sometimes I get a little bit behind, and sometimes I'll catch up. But the way the midterms are going to work are like this. So this is different than what I did in Chem 1A. So what I'm going to do is I'm going to have chapter exams. So for example, we'll do chapter 13, and then let's say you're on schedule, we finish it on September the 7th here. So if we finish chapter 13 on September 7th, then you can expect the test to be on the 14th. So I'm going to squeeze a test in here. Now the test is just going to cover 1 chapter. So it's going to be like 1 page long. Some people would call it a quiz. I'll just call it a midterm here. So you'll have an exam for chapter 13, let's say on the 14th here. If we finish chapter 15 on the 19th, then you can expect the exam like on the 26th. Does that make sense for that? And so it'll be like an hour, the test, an hour and a half, a page. The page will consist of some multiple choice and maybe a free response or 2 in there. But we're going to have a lot of tests. And so our first test is going to cover reactions and nomenclature. Maybe I'll group these 2 together, or maybe I'll keep them separate. Let's see what I'll do. I'll let you know soon. But anyway, our first test or quiz will be reactions and this nomenclature for 2 small quizzes. All right, is there anything else? Yeah, let's take a look at what else we That closed it. It didn't download it. Okay, also on the syllabus tab here, there's course info. Let's take a look at course info here. I'm going to download it. All right, here's my contact information. My office is in room Chem 120 down the hall, where I can be reached by email, arshab@elcamino.edu, or phone, extension 3240. The masteringchem.com, this is the website for our textbook, Petrucci. And then I included the catalog, course description, course objectives here. You can read through those. I have some SLOs. These are required by the state. There are actually too many SLOs to list and write. So these are just two very basic SLOs. So you don't have to pay much attention to these. SLOs stand for Student Learning Outcomes. Prerequisite, Chem 1A. Okay, required materials, Petrucci's, our textbook, the 11th edition. Well, but there's very little difference between the 10th edition and 11th edition, so you can get by perfectly well with the 10th edition. Even earlier editions like the 9th edition work. So I assume everybody's gotten the book? All right, this one you're not going to be able to get. This is our lab manual, but it's not available at the bookstore. And so don't bother looking for this. What I'm going to do instead is I'll just post labs on Canvas. So item number 2, strike. Item 4 you should get. That's a composition book. That's what we're going to use for lab. So here's an example of one from previous class, the lab notebook. You don't have to get one this big. This is a 8.5 by 11. You get the smaller ones if you want. It's fine. One thing that's nice is if you could get it with graph paper, it makes it easier to make tables this way. And what we do with the composition book is we write our observations. And so here, let me show you an example of what this student did. You know, there are different ways that you could do this. So an example would be they wrote the procedure on the left side here in one color of ink, and then they wrote their observations on the other side here with a different color ink. And so this makes the lab go much smoother. If you do some preparation before lab, that is, you just summarize the procedure. This is a bit much, but you know, it's a lot simpler to go through, like here, plus 10 DI, that's plus 10 drops of deionized water. Rather than reading a full sentence, they can go through this quite rapidly. This is an extremely long procedure for this particular lab. And so we're going to need a lab notebook like this. That's required. Safety goggles. The Chem 1A safety goggles are fine. If you don't have a pair, we probably have an old pair sitting around you can use. Scientific calculator. I recommend not the base model. You know, the cheap one used to be under $10. You want the $15 one, or what used to be $15. Maybe now it's $20. But you want the one that does or has an equation solver. You want the one that does quadratic equations. You want the one that does quadratic equations because you don't want, unless you're fast, you don't want to have to do quadratic equations over and over again. It's much easier if you have a solver that you can just plug in A, B, and C and then have to calculate x1 and x2. And so most of these, like the 15, well, I better check the price because I'm sure the price has gone up. But it used to be the $15 calculator would solve up to cubic equations. like third order, ax cubed, etc. Those are, once in a while we'll run into those too, so it's nice to be able to do those using the calculator. It doesn't go any higher, and so fourth order, fifth order, we have to solve by other means. So a scientific calculator that does quadratics will save you a lot of time. 7, a Sharpie is nice to have. I have some, that you can use as loaners, but it's nice to have your own. That way you don't have to look for it. Can you guys read this in the back? Is it too small? It's okay? All right. Recommended materials, lab coat. I lost my lab coat, so I didn't wear it during Chem 1A, but normally I wear it. So, but it was in the drawer over here. I didn't check there. But this is a $15 lab coat I got off Amazon. This is perfectly fine for this. All you want is something that protects you from splashes. So oftentimes what would happen to me is I'd get home and then throw the clothes through the laundry and notice there were a whole bunch of holes in my clothing where the acid might have ate up the cotton. And so if you have a lab coat like this, you can, it stains or whatever, or acid or base, it doesn't really matter. At UCLA, they require lab coats, but they require for spills and they require for fire protection too. So this lab coat would not be acceptable at UCLA because it does have synthetic materials. What they want at UCLA is 100% cotton lab coat. 100% cotton lab coat, when I was at UCLA as a student, cost around $60 or $70. And so the same lab coat now costs like $140 or something. But there are cheap cotton ones as well, 100% cotton, that I saw on Amazon for like $70, which would be good. But they don't last too long, so something like this is fun. Okay, the other recommended item are nitrile or latex gloves. I use both. I much prefer nitrile. One, nitrile gloves are a lot more comfortable. They breathe a lot better. But if they're more comfortable and breathe a lot better, do they offer as good of protection as latex? And the answer is they offer better protection than latex. The nitrile gloves are less permeable to a much larger number of chemicals than latex gloves are. And so nitrile gloves are all around much better than latex gloves. But nitrile gloves still aren't perfect. There are a lot of chemicals that just go right through nitrile as if you're wearing nothing. You have to be careful. Certain chemicals can easily permeate the material. So sometimes what we'll do is triple up on gloves. When I was doing some chemical reactions, I wore three pairs of gloves to help protect me. There was apparently there was one research professor, I forgot at which school, I think it was like Michigan or someplace like that. She was wearing 2 pairs of gloves. And what had happened was a very toxic compound hit just 1 drop or 2 drops. It's hard to tell because this is all, I think she documented some of it before she died, but anyway, I think about 2 drops of methyl mercury hit her glove, which she immediately removed and washed her hands, just standard chemical hygiene. But enough got through the gloves and into her skin to cause her to fall ill. And then about a week later, I think she passed away due to poisoning, of mercury poisoning, unfortunately. So even when you have gloves, you shouldn't have this false sense of confidence that it's going to protect you from everything. You have to watch out. And they have charts. So for example, if you're working with a specific chemical, they have charts to tell you how many minutes you can wear this glove for this particular chemical. Some gloves, in a second they're done. Other gloves, you can wear them all day and still be protected. Normally when I was working in the lab, I changed my gloves maybe 2 or 3 times during the day, just to be safe. Required assignments, all the assignments are required here, including lab, exams, quizzes, etc., and check out. So even if you drop the course, you still have to check out a lab, otherwise they'll put a hole on your transcript. So just be aware of that. Attendance is also required. Attendance, especially for lab. This is due to our articulation agreement with the UCs in Cal State. For example, at UCLA, they have a separate class, lecture and lab. Lecture is 3 units, lab is 1 unit. And so you could take lecture and not even bother taking lab there. But since we have it combined into one 5-unit course, then the way they want it to work is if you fail lab, I have to fail you from the course. And when we look at the percentages here, the total points, this is tentative, I'm thinking it's going to be about 1,030 points at the end. Of that 1,030 points, 230 points will be lab. And so, in theory, you could skip all the labs, not even show up and still pass the class. In practice, you won't. Because if you don't show up to lab, then I have to fail you, regardless of what your other percentage is. And that's because of our articulation agreement. And so you're going to have, out of this 230 points, I have to treat this like a separate class. So out of that 230 points, you have to get at least 65% of those points in order to pass this class. And so pay attention to that there. All right, so I'm having a lot of exams each chapter. So there's going to be 9 exams at 50 points each. And so that's incorporating reactions and nomenclature into one exam. And then at the end of the semester, we run out of time. So if we finish, let's say, chapter 25, I don't want to give the chapter 25 exam and the final exam on the same day. So what I'm going to end up doing is just combining the chapter 25 material into the final exam here. And so this isn't all the chapters that we're covering here, 9. Sprinkled in there will be some quizzes. These are going to be very short quizzes. These exams are just 1 page, like an hour, hour and a half. The quizzes will just be like 5, 10, 15-minute quiz. And we'll have about 10 of those. Then we're going to have homework. This is going to be 100 points. This is going to be 10 points each. There are actually going to be 11 homework assignments, but I'll just count the best 10 out of those 11. The labs, most of them are worth 10 points per experiment. In the experiment, you come in, you do the lab, and then you fill out a report sheet. The report sheet, you just fill in the blanks, do some calculations, write down some observations, that kind of stuff. Some of the labs are a bit more involved. For example, this one, QUAL, this stands for qualitative analysis. Qualitative analysis we're doing over 4 or 5 lab periods. Since we're doing so many days of qualitative analysis, I made it worth twice as much, 20 points. Okay. And then I have this one, SYNTH stands for synthesis. We're going to do a synthesis lab, and that's going to be worth 50 points. But the synthesis lab, the reason why it's worth so much is it's just maybe a 2.5 day lab, but it's worth so much because we're going to write a formal scientific report for this synthesis lab. And the same goes for the titration. Titration is a 2-day lab, but we're going to write a formal scientific report for that. So we're going to do 2 formal scientific reports. One for the synthesis lab, one for the titration. That's going to be a little bit different than filling in the blanks in the report sheet here. We're going to have it in a standard format, which includes things like abstract, etc. We'll talk about it more when we get there. And then the kinetics lab, there's quite a bit of computer data manipulation for the kinetics lab, so I made that worth double here, 20 points. This is the grade breakdown. I don't curve these here, but I might curve this, the overall percentage here. And so this cutoff for the A might drop a little bit from 90%. Same thing with the cutoff for the B. It might be curved depending on how hard to make the test. The cutoff for the C is not going to be curved, though. That's going to stay at 65. That's already a wide percentage. Most people go to 70% for a C. And this is just a wider range here. All right, a note on cheating. You know, of course, academic honesty is expected. If you have any special requirements, let me know. The changes, if there are any changes to the schedule or whatever, I'll try to announce those in lecture. Okay, and then I finished this off with the definition of chemistry. Let's take a look. This is from the American Heritage Dictionary here. And so if we look at definition 1, the science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. So that seems like a pretty good definition. We'll go to number 2, the composition, structure, properties, and reactions of a substance. So that seems pretty good as well. So 1 and 2 here. Although I'd probably change it a little bit. The way I change it is I'd probably say the composition, structure, properties of matter. Probably say that. You know, that gives a more broad definition versus a substance for atomic or molecular system. Just call it matter. And I'd probably get rid of reactions. Do you know why I'd get rid of reactions? Well, I really wouldn't get rid of reactions, but when chemists think of properties, what two types of properties come to mind?
Chemical and physical.
Chemical and physical. And chemical properties, what are chemical properties? Well, chemical properties are what chemical reactions does it undergo? You know, what does it react with? And so when we think of properties, well, reactions are properties. And so this is redundant. So I'd get rid of reactions, just call it properties, and both the properties would encompass physical properties and chemical properties. All right, any questions on this stuff here? All right, so physical properties aren't too bad. You know, when we think about physical properties, what are some physical properties that you can think of? Size, shape, color, smell, taste. Yeah, all physical properties. Those are good. Density is another physical. Boiling point, melting point, etc. So there are a lot. Refractive index, a bunch of them. When you think of chemical properties, what comes to mind? So let's look at HCl. Hopefully you guys remember the name. I mean, summer's been... Did you guys have a good summer? You guys remember the Chem? Did you take Chem over the summer? Chem 1A over the summer? Anybody take Chem 1A over the summer? So this should be fresh. You had Chem 1A last year. It might not be so fresh, but everybody should know HCl. What's the name of HCl? Hydrochloric acid. Hydrochloric acid is when it's mixed with water, but do you know pure HCl? Pure HCl, do we call hydrochloric acid or do we name it something else? Pure HCl. Pure HCl we call hydrogen chloride, and it's a gas. So sometimes we'll just call it gaseous hydrogen chloride. And so one of the physical properties of pure HCl is it's a gas. Another physical property of HCl is it dissolves in water. Why does HCl dissolve in water? What would you say? HCl dissolves in water, and we say it's very soluble in water. Why is HCl so soluble in water? And then we make HCl8Q. HCl8 aqueous hydrogen chloride, which is hydrochloric acid, which is a strong acid. And we can get lots of HCl to dissolve. In fact, do you know what the solubility limit is for HCl? How many moles of HCl I can cram into a liter? Do you know about how much a mole of pure HCl gas weighs? Roughly? Well, the molar mass of chlorine is 35, hydrogen's 1. So it's about 36 grams of HCl in a mole. So how many moles of HCl can I get? Is it infinite? You know, usually if something's infinitely soluble, we call it miscible. You know, they like each other so much. Have you ever heard that term, like dissolves like? Like dissolves like? This is why HCl is so soluble. HCl is so soluble in water because it's kind of like water. In what way is it like water? Water is very,
Polar.
polar, yeah. Water is very polar, HCl is very polar, like dissolves like, it's very soluble. But it's not infinitely soluble. There are some things that are infinitely soluble, and when something's infinitely soluble, we call those what? We use the term miscible. Have you heard of miscible? Miscible means soluble in all proportions. And so it's infinitely soluble. HCl is not infinitely soluble. There's a limit. And that limit is what we call the solubility, you know, the maximum. There are two ways we think of solubility. One is quantitative. Now, what is the maximum? And two is qualitative. Qualitative is it soluble or not soluble? That's qualitative. Yeah. And so the limit is about 12 moles. You know, 12 times 36, 37 grams. That's a lot in a liter. You know, 10 times 30, 370 plus another 70, about 400 grams of HCl you can cram into a liter of water. And that's like a liter of water bottle. Now it weighs a lot more. Is that right? Well, anyway, the max is around 12 molar. So 12 molar HCl we call concentrated HCl. So what happens is this. Let's say you had a bottle of 6 molar, about half that, and you left the cap off. Do you know what's going to happen if you leave the cap off? So let's say I left the cap off for a week. I come back in a week, is it still 6 molar? No, it's going to be less, right? What's going to happen is some of the HCl is going to evaporate off the surface, right? And it's like if you had a bottle of sparkling water and you left the cap off and you came back a week later, is it still going to be sparkling? No, it's going to go flat. And so the same thing with your HCl. And so there are certain physical properties we should know. Like, for example, HCl. Can you see any color to it? No, it's colorless. This is a clear colorless gas. Very soluble in water, makes a clear colorless solution, a CCS we call this. There's a limit to how much. That's the solubility. But we can have things that aren't to the limit. When we're at the limit, it's saturated. When we're below the limit, it's unsaturated. And when we're at the limit, we call it concentrated. So 12 molar is considered concentrated HCl. 6 molar is considered dilute. Even though 6 molar is still pretty concentrated. Still pretty nasty stuff. But anyway, those are some physical properties of HCl. How about some chemical properties of HCl? Can you tell me some chemical properties of HCl? Uh-huh.
It's acidic.
It's acidic. In fact, it's a strong acid. It's good. Any others? Is that it? In other words, it's a strong acid? Or is there more to it than that?
Strong electrolyte.
It's a strong electrolyte. Strong electrolyte would be more towards physical end of things. But we'd look at that. Strong acid. All right, well, what do strong acids react with? Tell me everything that HCl reacts with. So, for example, does HCl react with platinum metal? No?
No.
How about gold metal? Does HCl react with gold metal?
No.
Copper?
Yes. I think so. Or no.
Copper is actually a no. It appears, it looks like it does react with copper, but it's taking the oxide coating off. How about nickel? Would HCl react with nickel? Iron? Cobalt? Etc. So what we can do is we can go one by one. If we go one by one, then it's going to be quite a long list. It'd be like listing physical properties. When we do physical properties, we do them one by one. You know, density, this, this, this. But when we do chemical properties, there's too many. You don't want to look at every single chemical and then say, does it react, does it not react? You know, yes or no. And so we don't want to do it that way. What we want to do is we want to look at the types of reactions that HCl undergoes instead. And so let's take a look at chemical properties and then try to, rather than looking at them one by one, we'll try to categorize them. So if you look at week 1 module here, I don't do PowerPoints that much. I never liked PowerPoints much. But for chemical reactions, I have some PowerPoints. So I have these 3 PowerPoints. And this is a handout here. And then here's some solubility rules from our book, table 5.1. So basically, this is the American Heritage Dictionary definition. I already talked about that. And then I talk about properties. When chemists think of properties, they think of 2 types, physical properties and chemical properties. So we're going to focus on the chemical properties, or i.e. the reactions, chemical reactions these undergo. When I think chemistry, this is what chemists do. Chemists want to understand properties, you know, whether they're physical or chemical. There are different ways we can understand the properties. One is we can just memorize them. What's the boiling point of HCl? Do you have that memorized? Or we just look it up. You know, we could look that up as well. Or 2, what we want to do is we want to understand this based on things like composition and structure. So for example, I ask you why, you know, I expect HCl to be very soluble in water. Well, it's very like water. Like water in what way? It's like water in the sense that HCl is quite polar. So when I look at the hydrogen chloride molecule, this would be it. This is HCl. And when I dissolve it in water, well, there are certain other physical properties. It's a strong acid. And as Tristan mentioned, strong acids are strong electrolytes. So when we dissolve this in water, do we find HCl molecules dissolved in water, or what do we find in water? Here.
H plus and Cl minus.
Yeah, H plus and
Cl minus.
Cl minus. But what's happening with the H plus is the water molecules. The water molecules are going to pluck off the H pluses to make H3O plus. So we'll form some hydronium and some chloride. Like this. See, the hydronium, the structure of that, the composition is 2 hydrogens, 1 oxygen, and a positive charge. Structurally, it's going to have a Lewis structure that looks like this. Now, the Lewis structure, you know, we know about the shape. You know, this is not a T-shaped molecule. What shape is this? I'm sorry? Tetrahedral. It's a tetrahedral electron geometry, like electron pair geometry. But the molecular geometry is just looking at the atoms. So if you just look at the atoms, what is the shape? Yeah, trigonal pyramidal, this would be. And then chloride looks something like this. And then there's a charge here. Like this oxygen has a charge which will circle like this, and the chloride has a charge, I'm going to circle like this. So the chloride's going to have a -1 charge. Now this oxygen has a positive charge. What do we call that charge there? We call that charge well, how many different kinds of charges do we have? Do you know how many different kinds of charges we have? we have the total charge or the net charge. We have something called the formal charge, another thing called the oxidation state, and another thing called the dipole or partial charge. This is called a formal charge here. So the formal charge on oxygen is +1. Gives us a net charge. The formal charge on the hydrogen is 0. We don't usually show those. On the chlorine here, the formal charge is -1. And so what we want is we want to know something about the composition, you know, what atoms, what elements it's made up of. We want to know something about the structure. So this would be trigonal pyramidal. This would be spherical here. These would be the structures of these types of things. And so in chemistry, we want to be able to correlate certain things. So for example, do you see any charges here, any formal charges here? No, the formal charges are 0. And so this has a 0 formal charge. This has a 0 formal charge. But formal charge isn't the only charge we look at. What other charge we look at? We look at oxidation state. So the oxidation state on chlorine here, do you know what it is?
0.
No, on this chlorine it's -1. Oxidation states I put in parentheses, and I'll actually write the 1 there. Do you know what the oxidation state on this oxygen is? What is the oxidation state on the oxygen in hydronium? It's not +1. It's not +1. It's different. -2 is correct. The oxidation state on oxygen is -2. So how can oxygen be +1 and -2 at the same time? Is that possible? Well, it depends on how we look at it. You know, but what we do is we're trying to analyze the structure. You know, we know the composition, we're trying to analyze it structurally. And these are the types of things we do when we analyze the structures of these. We want to know the oxidation states. The formal charge on the hydrogen is 0, but the oxidation state on the hydrogen is +1. So why the heck do we have 2 different numbers for the same atom? Can somebody answer that? Why is this oxygen +1 and -2? It can't be that at the same time. Does it switch, oscillate back and forth? +1, -2, +1, -2. Is it oscillating back and forth? Is that what's happening? No, that's not what's happening. What's happening is it's giving us 2 ways to look at the structure, 2 different ways of looking at the structure. Tristan, do you remember the assumption for formal charge and the assumption for oxidation state?
Yeah, oxidation state, the atom takes all the electrons. On formal charge, you break up the bonds.
Yeah, that's pretty much it, but you want to be a little bit more specific. With oxidation state, it's winner take all. In other words, we assume that the bonding is 100% ionic or covalent?
Ionic.
Ionic. And so what we're doing with oxidation state is we're imagining all these bonds as being 100% ionic. If that's the case, then these would be the resultant charge on the atom. Whereas with formal charge, we're doing the opposite. What's the opposite? Well, if it's not 100% ionic, then it must be 100% covalent. And so for formal charge, we assume all the bonds are 100% covalent and then look at the distribution of electrons. What we're trying to do is we're trying to imagine the distribution of electrons in the structure. So for HCl, this is not accurate. The formal charge is not really accurate, nor is the oxidation state, because this is what we call a polar covalent bond. So when we look at HCl, the formal charge is 0. What are the oxidation states? I should do the oxidation state. I should be consistent here and do them in the same color. But the consistency here is I circle formal charges. Now that's not a law, you know. It's not against the law if you don't circle the formal charges. A lot of people don't, but it's just a convention. And so I like to circle the formal charges and put oxidation states in parentheses. So regardless of the color I use, let's see. So these are formal charges. What are the oxidation states? So what's the oxidation state? You assume this is 100% ionic. Winner takes all. Who's more electronegative? When I say winner take all, they take the bonding electrons. If chlorine takes these two, we end up with this, which we call chloride. And then hydrogen loses those bonding electrons, we call it H+. And so the oxidation state is +1 for hydrogen, -1 for chloride. So we either assume it's 100% covalent, they share 50-50. It's even, we'll split it down the middle. The reality is it's not shared 50-50, right? The reality is that chlorine's more electronegative, and chlorine's going to pull the electron cloud closer to it. As chlorine pulls the electron cloud, it becomes polarized, like this. And it loses its symmetry. It used to be like cigar-shaped symmetry. Now it's asymmetric like this. That means we get a buildup of negative charge density on chlorine and a loss of negative charge density on hydrogen. So the reality is it's somewhere in between ionic and covalent, and we call it polar covalent. Well, what is it? If it's not -1, it's between 0 and -1. What's between 0 and -1? Well, we need the number for that. In order to get the number, we'd have to do some theoretical calculations. Do you know what is the theory that chemistry is based on? What's the theory called? The theory that underlies chemistry, the theory that provides the foundation for chemistry. Do you know what that theory is called? Starts with a Q. QU.
Quantum mechanics.
Quantum, yeah. Quantum. So we could do some quantum mechanical calculations and figure out the delta, what the magnitude is. But do you want to do any quantum mechanical calculations? Now, have you solved the Schrodinger equation? Anything like that? No. So what we do is we can do formal charge really easily. We can do oxidation state really easily, and it's somewhere in between the two extremes. We look at the two extremes. And so this is why we have two numbers. The two numbers we don't interpret the same. When we compare formal charges, we compare those with other formal charges. When we compare oxidation states, we compare them with other oxidation states. We never mix and match. The reality is it's going to be partial, somewhere between 0 and -1, somewhere between 0 and +1. And so that's our delta plus and delta minus. Why is it so important? Because chemistry, what's the most important force underlying chemistry? Is it, gravity? Are chemists mostly interested in gravitational pull between the atoms? No. And so do you know what force? Is it the weak nuclear force, the strong nuclear force? Is that what chemists are most interested in? No. Chemists are most interested in
Intermolecular force.
Well, they're very interested in intermolecular forces, but what force of nature are they mostly interested in? What other force? So you got gravity, you got weak and strong nuclear forces, and you got electrical and magnetic forces. And so chemists are mostly interested in electrical forces. This is why charge is so important. charges and charge are most important. And this is why you should review. Review formal charge, review oxidation state, review polarity, this kind of stuff. That'll help you in understanding structure, which will help you better understand properties. So we want to do that. All right. In fact, let me talk about theory. What is a theory? Or let's talk about the scientific method. Somebody remind me the scientific method. You know, just the standard scientific method. I mean, science can proceed in different paths, different pathways, but this is typical for working scientists. Working scientists doing this kind of stuff here. What types of things or steps? There we go. So let's look at the steps in the scientific method. What would you say the first step in the scientific method is?
You have a question?
Okay, if you have a question, that's good. But does it always have to start off with a question? In order to do science, do you always need a question? No. What if I didn't have no questions? I mean, I'm just kind of interested in certain things. Like, let's say an apple fell from the tree. Yes. And one thing you could do is you don't have to have a question. You could just observe it, you know, an apple falling from the tree, and you observe it. And so normally, sometimes we don't know what questions to ask, and we just take observations, and then sometimes we can generate questions. But what we do is we take observations. This is typically what I did. Take observations, and then do what? So we can have a lot of observations. HCl reacts with this, but doesn't react with that. HCl displays these physical properties, which are different than those physical properties. And so those are observations. And then the questions might arise from that. You know, why does HCl react with this but doesn't react with that? Those types of questions come up. But first we need to see some observations to see how it behaves, you know. Because if you take something like malonic acid, you may not know how or what questions to ask. And you might just take observations to see how it behaves. So we take observations, and then what we do, since a lot of you didn't have me in Chem 1A or Chem 4, we look for patterns and trends. So is there a pattern to the observations? If there's a pattern to the observations, then, and this pattern's reproducible, and simple patterns we can define mathematically, and we end up generating a law. And so we might observe how gases behave with temperature. We observe how gases behave with temperature, and we see a pattern or a trend, and then we can come up with a law, Charles' law. Charles' law says how the gas volume behaves with temperature. But then we might dig a little deeper. You know, we might want a more fundamental description of what's going on. And, or we might stop here. We can use laws to make predictions, so we can go both ways. Once we know how the gas behaves, then we can predict these patterns, and we can predict these observations. But we might want a more fundamental, like for example, the ideal gas law. Ideal gas law, PV equals nRT. You've memorized it, right? But where does it come from? Well, maybe it comes from a combination of the simpler gas laws, but where do the simpler gas laws come from? You know, and so you might want to think, okay, PV equals nRT, we might try to think a little deeper. You know, these are all what we call empirical from observation. And we get to the law, and then we might go a step further into a hypothesis. A hypothesis is a tentative fundamental explanation, and those tentative fundamental explanations can evolve into theories. So what a theory is one, it's a fundamental explanation of the observations, trends, patterns, laws. It's a fundamental description of what's going on. So if you understand things at a fundamental level, you know, what's going on with the structure, what's going on with this, then we should be able to use the theory to predict, okay, I want to predict what reactions HCl undergoes. Will HCl react with platinum? Why not? You know, that's what I'd like to know. And one other thing a theory should do is it should be able to predict new unforeseen results. And so we want to be able to use a theory to make predictions. So the scientific method, we see this in action all the time. So for example, there were two competing hypotheses for, let's say, COVID-19. Did you hear that? Some people looked at the observations and they came up with a hypothesis that it came from bats through the wet market. Other people looked at the observations and they came up with an alternate hypothesis. The alternate hypothesis was it must have come from, you know, the Wuhan Institute. And so those were two competing hypotheses. And those, you know, are going to be based on the interpretation of the observations, the patterns. We don't have to have a law, you know, the law of the COVID virus. You don't have to have that. But eventually we want to come up with a theory. The theory is going to have a general acceptance. That is, the hypothesis is tentative. What makes it go from tentative to a theory is that it has to have widespread acceptance. And this is the way science works. So science works, there's not one person that dictates what's right in science and what's wrong in science. Science is like a collective approach where, you know, the bad science is usually filtered out. The bad science is filtered out because it doesn't make it this far. You know, they're trying to prove this hypothesis. The hypothesis would be, you know, for example, there are certain hypotheses. Let me use it. Well, actually, let me go back to this and then I'll use another example here. But eventually what we want to do is we want to iron out which hypothesis is stronger. Why? Because we want to understand the theory. You know, was the lab leak theory correct? Or was the wet market theory correct? Why do we want to know that? So we can predict. We want to predict so this type of stuff doesn't happen again. Right? And we aren't going to be able to predict until we have some kind of consensus as to what happened, the fundamental description of what happened. But we see this over and over. For example, in thermodynamics, you know, the laws of thermodynamics were generated well before quantum mechanics. They were generated even before atoms were hypothesized. Or actually, atoms were hypothesized a long time ago. They were generated before atomic theory, let's say, before there was widespread acceptance of atoms. But the laws of thermodynamics have withstood the test of time. So, for example, one of the laws of thermodynamics is you can't build a perpetual motion machine. But on eBay, you can buy a perpetual motion machine. But, you know, eventually those have been found to be bunk. That is, they get debunked. And so that would be the scientific method in action. So some laws are very, very sound. They haven't found any violations in the laws of thermodynamics for a couple hundred years now. Other laws aren't, like the ideal gas law. Are there any violations of the ideal gas law? Is the ideal gas law, do you have 100% confidence in the ideal gas law in supplying you the correct answer? 90% confidence, 95% confidence? What's your level of confidence in applying the ideal gas law? A 100%? You'll get the right answer? 90%? Less than 90%? And that's going to come because of this. Some laws are like carved in stone. Other laws, there are going to be exceptions. Ideal gas law is one of those. You know, ideal gas law versus real gas. If you're dealing with real gas systems, ideal gas law is going to give you the wrong answer. And so you have to be careful. But overall, if you limit the scope That is, if you limit the pressure and the temperatures to certain ranges, then the ideal gas law works pretty well. If you're outside those temperature and pressure ranges, then don't use the ideal gas law. Use a real gas law. Real gas law like the van der Waals equation, a real gas law like the Burg-Real equation. We want to use a real gas law instead of the ideal gas law. This different than rules. Rules, there are a lot more violations. We'll be talking about laws, rules, and other things. So rules are way down the hierarchy from laws. But laws aren't always perfect. And so some laws have to be modified. The same thing happens with theories. Some theories have to be modified as well. All right, so this is the basic foundation. Now what we want to do is we want to understand properties. We want to understand properties, these patterns and trends, you know, that's what I'm going to call the properties over there. And there are two ways to understand it. One, we can understand from observations. These are just empirical. You just measure it and see what happens and just remember it or write it down. The other way we want to understand these patterns and trends is from theory, theoretical. And so this is kind of your memorization and this is kind of your theoretical derivation end of things. Unfortunately, we have to use both. We can't do everything from theory because the theory is too complicated. The theory is quantum mechanics, and quantum mechanical calculations are quite complicated. And so we're going to understand a lot of chemistry based on observations. And so let me talk about this slide, and then we'll take a break. So our two-pronged approach is a mix. It's going to be a mix of theory and descriptive chemistry. Descriptive chemistry is just the observations. The theory as much as we can. So we call this Lewis theory, Lewis structures. Do you remember all that? You know, Lewis theory, Lewis structures, that's not really a separate theory. That's just an application of quantum to Lewis. You know, we have the valence electrons, we have all this stuff. We have lots of little theories based on quantum mechanics. So Lewis theory comes from quantum mechanics. Do you guys remember valence bond theory? Valence bond theory, which is Lewis theory essentially, comes from quantum mechanics. Do you remember molecular orbital theory? Do you remember kinetic molecular theory? All those are based on quantum mechanics here. But we just have these sub-theories that are part of the overall collective whole. And so the more we understand this theory, the less memorization we have to do. And so what we want to do is we want to start analyzing the structures and compositions theoretically as much as possible. And so we're going to go back and look at these types of things later. Some things are much easier done descriptively, like is HCl a gas? I wouldn't want to do that quantum mechanically. You know, the calculations would be too much of a headache. I'd just rather know that HCl in pure form is a gas. What color is HCl? It's colorless. That's memorization. So once we get a better idea of this, we can use this type of material in two ways. One, you know, we can use properties to determine composition and structure. So for example, let's say there's a big earthquake and there's no water, but there's some water in this bottle. Would you drink it? Say you're really thirsty. Would you drink it? Well, if this were a geology lab, don't drink it, because you know, in geology, we used to carry bottles like this. Did I say this earlier? We used to carry bottles like this, and we have a belt, and we'd hook it on the belt. And do you know what we filled the bottle with? We filled it with hydrochloric acid. Why? Because when you're out in the field, you want to start spraying. You spray rocks, you spray minerals with hydrochloric acid, and you look for effervescence. If you see effervescence, then we know it's a carbonate-based rock or carbonate-based mineral. And so that's using one of the chemical properties. So if you're in a geology lab, I probably wouldn't drink it. This is a chemistry lab, so would you drink it? Would you? Maybe. Maybe not. I don't know. But how would you tell? Well, one thing you could do is you could look at its properties. You know, if this stuff boiled at 88 degrees Celsius, would you drink it? No. If it boiled at 105, no. If it boiled at 100, maybe. You know, that's looking promising. And then you look at other properties, and eventually you look at so many properties that you can surmise that this is pure water. If it's not, if it's too difficult, you know, maybe there's trace methyl mercury in here. If there's trace methyl mercury, don't drink it. You know, what you probably want to do is distill it. and separate it, purify it. And that's what we can do. So we can use properties to determine what it is. You know, what's its composition? Is it water? No. Or, and this is what we're going to be spending a lot of time on, we could use its composition and structure, like HCl, and determine its properties. You know, what are its chemical properties? And so that's what we're going to spend most of the time on here. Looking at the composition and structure and trying to determine the properties. So physical properties, we can come up with an easy list for those. Chemical properties, these are the chemical properties from Chem 4 and Chem 1A. So if we're going to look at HCl, and we want to categorize this in terms of properties, then should we look at the combination, decomposition, acid-base, single replacement, double replacement, combustion, precipitation, reactions? Here. And my answer is no. I'm not going to use this categorization scheme. I'm going to use a totally different categorization scheme. And the reason for that is that this is kind of confusing, and then there's some overlap here. And it's not, I don't think this is the best categorization. If I want to know the chemical properties of HCl, I'm going to look at 3 different types of chemical reactions. And these are the 3 basic types of chemical reactions. And this is going to cover all these here. And so we'll talk about that next. So what we'll do is we'll just go on a break here, and then we'll start up. Let's take a look. The syllabus here. Next week we're doing lab reactions worksheet on Wednesday. That's dry lab, so there's no experimentation. On Monday, September 11th, we're going to have lab check-in, and then on September 13th, we're going to have our first lab. This you'll need safety glasses, closed-toe shoes, etc. And so we'll start wet lab on the 13th, which is the 3rd week. So this classification scheme, in Chem 4 you're supposed to memorize a whole bunch. You know, different combination reactions, etc. These are just different patterns that you see. Some of these are very useful, and so we'll know those, and we can use them, but we're going to organize this totally different. We want something more general. So for example, if you saw an equation like this, HCl, you say this is strong acid. What about HNO3? What are the chemical properties of HNO3? Is that also a strong acid? Yeah? Or weak acid? What is it? One of the things that you might consider doing, especially if you're pre-med or something like that, is eventually you'll have to take a test, the MCAT. And in the MCAT, you're going to have a lot of chemistry questions. And this is a story that happened to my friend. When I was at UCLA, I was a chem major, so my friend asked me for help reviewing chemistry. He's about to take the MCAT. So I started reviewing. But he hadn't had chemistry in 2-3 years. General chemistry, 3 years. And he forgot everything. And so I said, okay, I'll help you. But unfortunately, he forgot everything. I mean, he didn't remember anything from chem. And so we had to start from, like, day 1 of Chem 1A, or it was bad. And there wasn't enough time, because not only did he have to study and review chemistry, but he had biology and a bunch of other stuff he had to do. And so what he ended up doing was he just decided not to take the MCAT that year. And he took a gap year, and then he took another gap year. And during these gap years, all he did was study. He just reviewed all the material. And so it happens. It's easy to forget. It's easy to forget if you never use it. And so one of the recommendations from a memory expert, I listened to his, I bought a course from him. And he had a little system, like for example, if you need to remember something, then you should review it. So after you finish the class, review it, let's say once a month. And this works like reviewing your notes. You don't review the whole book, it'd be too much to read, but you can review your notes and just refresh your memory. And then he would do that once a month, and then eventually it'd go to once, every 3 months, and then once every 6 months, and then once a year. And that way he could remember this stuff. And so if you're planning to take the MCAT, you'll probably want to do that too. Otherwise, you're going to be in the same boat my friend was. And that was, he had to start over again. But HNO3, do you guys remember the 7 common strong acids? Did you have to memorize those? I know Tristan had to, but did your instructor make you memorize those? No? Well, normally I have all my students memorize those. And so HNO3 is one of the 7 common strong acids. So it's also a strong acid. So does that mean HCl and HNO3, they're both strong acids, so they both have exactly the same chemical properties? One time, I was driving on the 101 and there was a tanker wreck. And the tanker wreck, and a whole bunch of acid spilled out. And I was like the 3rd car behind, so I could see the news crew there. We were still a couple of thousand feet away. And the news crew, the guy was saying, oh, we had an HCl, hydrochloric acid spill in the freeway. But I looked at it and I said, no way could that be hydrochloric acid, because there are big plumes of orange smoke coming off of it. And how could it be HCl? HCl would be plumes of colorless vapors coming off. And so it was not HCl, but it was corrected eventually, but it gave the impression that it was a hydrochloric acid spill. Instead, it was not hydrochloric. Do you know what it was?
Nitric acid.
It was nitric acid. Even nastier. Now, why would nitric acid, aren't they both strong acids? Why would nitric acid be even nastier? Uh-huh.
When it's evaporating, it produces, what is it? Nitric oxide or something?
Okay, yeah. It can decompose and form some nitric oxide. Nitric oxide's colorless.
Oh, I don't remember what's the brown one.
The brown one's nitrogen dioxide.
Oh, okay.
Or
Yeah, and that one's the nasty.
NO2. NO2. Both are nasty. NO nitric oxide isn't as nasty. And we all need nitric oxide for blood regulation. Nitric oxide won Molecule of the Year in Science a couple of decades ago, I think. But anyway, those are 2 distinctly different properties, chemical properties of HCl or physical properties of HCl, but they're both strong acids. But if you're given, I gave this reaction, I think on Chem 1A, and a lot of people left it blank. A lot of people left this reaction blank because they didn't know what to do, because it didn't fit one of these patterns. They might have been experts at this. They might have said, okay, is that a combination reaction? It doesn't look like. Is it a decomposition? Is it acid-base? Is it single replacement? Is it double replacement? Is it combustion? Is it precipitation? No, it's none of those. And so what is it? It's one of these. Well, what is one of these? And if you don't know this pattern, can you figure it out? And so this is a very famous reaction. Does anybody know the name of this reaction? It has a name. Uh-huh.
It's when you combine HCl and HNO3, it creates aqua regia, which can dissolve the platinum group.
Yes. Right. I asked you, will HCl dissolve gold? No. It turns out, will HNO3 dissolve gold? No. But a combination of HCl and HNO3 is called aqua regia, and aqua regia will dissolve gold. And so that's one of the chemical properties of aqua regia. So should you memorize this? No, actually, this is a combination of 2 types of reactions here. And these 2 types of reactions we'll talk about. And so it's a lot easier to understand based on a more general picture. Rather than trying to memorize individual patterns, we look at a more, or at least a wider view, a more comprehensive view of reactions. Sometimes that categorization seems a bit confusing. So for example, if we look at this one, this is a combination reaction. A plus B yields AB or something like this. But we look at the second reaction here, this also looks like a combination. We're combining 2 to make 1. We're combining 2 to make 1. So are both these reactions the same? No, these are totally different. The first one is what we'd call, let's say, a combustion reaction. We're burning carbon or combusting it to form CO2. The second one, is that a combustion? No, the second one, this is a bit trickier. This one is a combination, but we call it a Lewis acid-base combination. And so the scheme is not very effective, I think. And so what I want to do is I want to change the classification system. So this is what I call the alternate classification system. We're going to have 3 basic types. And these 3 basic types are categorized based on driving force. So all metathesis reactions will have the same driving force. Not exactly, overall the same driving force. This is driving force for metathesis. Acid-base will have acid-base driving force, and oxidation, reduction, or redox will have redox driving force. And the driving forces are different. So for example, the driving force for metathesis might be precipitation, but precipitation is not a driving force for redox. Here. And so it's going to be based on 3 different driving forces for 3 different types of reactions. And those are the reactions that form a comprehensive list of chemical properties. So in theory, what is the driving force? In nature, what we tend to do is we tend to go from less stable to more stable. Higher energy to lower energy. That's the natural progression of things. They'll go from high energy to low energy. And so we call that, as far as thermodynamics, we call it going from less thermodynamically stable to forming more thermodynamically stable, and we're going to call that our driving force. We're going to lower the energy. In terms of descriptive chemistry, things like forming a precipitate. Precipitates are quite stable solids, crystalline solids. Forming a weaker acid from a stronger acid. So if we go from a stronger acid, like one of the 7, or it doesn't even have to be one of the 7, it could be a weak acid, but it just has to be a stronger weak acid, and we're going to a weaker weak acid, that constitutes a driving force as well. Or formation of a gas, it's another driving force. Because in nature tends to do 2 things. 1, we minimize energy. We go from higher energy to lower energy. And 2, we maximize entropy. Entropy is this measure of disorder. It's talked briefly in Chem 1A, but we'll look at it more in Chem 1B. But what we want to do is we want to maximize entropy, that is, maximize the amount of disorder and minimize the energy. We'll look at the entropy later. We're primarily going to focus just on energy. So when I asked to predict the chemical properties, what I want to know is what are the metathesis properties of HCl, what are the acid-base properties of HCl, and what are the redox properties of HCl. And then I'll have it all covered. Well, how do all the other reactions fit into this scheme? Well, here I have my 3 basic types of reactions: metathesis, acid-base, and redox. For metathesis, I give different kinds of reactions, but the simplest metathesis is double replacement. It's the simplest to recognize. But it doesn't have to be a double replacement. It could be an ion combination. So for example, if I like the chloride in HCl, if I take the chloride in HCl and react it with silver ions, do you know what forms? Well, chloride and silver ions like each other, and it's going to form AgCl. AgCl is a solid precipitate. Solids, precipitates like this are more thermodynamically stable. So this is what we call a driving force. The driving force is the precipitation. DF stands for driving force, PPTION stands for precipitation. And so the driving force for this is precipitation. We call this a metathesis reaction. However, I could write this like a double replacement. I could take HCl aqueous and react this with AgNO3 aqueous. And so the chloride ion I'm getting from HCl, hydrochloric acid. The silver ion I'm getting from silver nitrate. And so this is an AB plus CD. This AB plus CD is going to give me HNO3, nitric acid, and AgCl solid. And so the driving force for this is precipitation. This is a double replacement reaction, or metathesis. I call it ion combination because essentially that's what's happening. We're just combining ions that like each other, silver ions and chloride ions in this instance. All right, if I'm not locked into an AB plus CD pattern, then I can look at other reactions. For example, this. So I throw in, all I do is I throw in a reaction like this here. I might go HCl plus KNO3 plus AgC2H3O2 yields what? And so some people will see this reaction and they'll go, wow, that doesn't fit any of my patterns. Or maybe it does. You know? If you were given this with 3 different reactants, what would you do? Well, what you could do is, you know, I've given this type of problem on test 2, and then people just give up on it because they don't recognize the pattern. You don't have to recognize the pattern. What we could do is we could do maybe double replacement with these 2, double replacement with these 2, double replacement. We try all combinations of double replacement. Or we do what's called an inventory of ions. I'll take an inventory and see which ions like each other. And so HCl is going to have the H plus and the Cl minus, or the hydronium. Hydronium and H plus I use interchangeably. And then I have potassium ions, I have nitrate ions, I have silver ions, and I have acetate ions. And then I look at which ions like. Well, silver and chloride like each other. They're going to form a precipitate. So I could do something like that. This is ion combination. And so it doesn't have to fit this double replacement form. So I don't want to be locked into thinking double replacement. It could have a different pattern, but still be a metathesis reaction. And so this is why I call it metathesis and not double replacement. But essentially they're the same thing. We're just looking for favorable ion combination. So metathesis or double replacement, you swap the ions and see if you make a more favorable combination. That's it. And so we've already done these in 1A. For acid-base, we have 3 types of acid-base reactions. We have Arrhenius, but these are based on the definition. Arrhenius is the most restricted definition of an acid. Arrhenius acid is just H+. Arrhenius base is OH-, but not all bases are OH-. For example, ammonia. Ammonia is weak base, and therefore we have a wider definition, or more broad definition of an acid base, and that's Bronsted-Lowry. You know, Bronsted bases are proton acceptors, so ammonia could be a Bronsted base, proton acceptor. It doesn't have to have hydroxide. But there are some acids that don't fit either of these. They're not Arrhenius, they're not Bronsted. And therefore we have the widest definition of an acid and base, and the widest definition is Lewis. A Lewis acid is an electron pair acceptor, a Lewis base is an electron pair donor, and that's the most broad definition. So there are some things that are a little weird that we consider acids. So, for example, CO2. CO2 is a gas. Would you consider CO2 an acid or a base, or neither? Normally we consider neither. There's no proton to donate, there's no proton to accept. And so normally we think of CO2 as neither being an acid or a base. But it turns out that CO2 is actually an acid. This is a Lewis acid. And so in Chem 1A, I didn't spend much time talking about Lewis acids and bases, a little bit. In Chem 1B, we're going to spend a lot more time looking at Lewis acids and bases. So we'll look at weird species like CO2 and others. And so acid-base. And then we have redox. Some common redox, I'm missing one here. Single replacement. We had skeleton redox is this thing where you're balancing out the oxygens by adding water, balancing the hydrogens by adding H+. This is at the end of chapter 5. Then I have something called the redox chart method, which is more like chapter 20. And then combustion, I forgot to put combustion in here, but I needed et cetera because they're more. So combustion, et cetera. do those. We're going to have some assumptions here that we're going to make. So for example, I don't know if I told you this, but in high school, when I was taking high school chemistry, my high school chemistry teacher said, okay, I'm going to drink HCl, hydrochloric acid, with one caveat. He said, first he's going to add some sodium hydroxide, and then drink it. Well, then the chemistry there was, okay, first he's going to take the HCl, and then he's going to neutralize it with some sodium hydroxide, and sodium hydroxide plus HCl makes what? Salt water. So he's going to drink the salt water. So that was the big joke. He's going to drink salt water. And so all year long I was waiting for him to drink it, and he never did. I was so disappointed because I wanted to see it. But then as I was continuing chemistry, I was thinking about this, and I drink HCl all the time. You might drink it all the time too, because do you know what the pH of our tap water is?
In Torrance, it's actually around 8 point something, because I kept fish for a while and I would always say pH.
Oh, really? Wow, that's pretty high.
Yeah, it's like 8.3 or 8.4.
It could be because of your piping or something else. You know, the tap water here, with the
I
pH
checked online and all the reports say it's around 8.
around 8. You know what our tap water is here? Or actually our DI water? Our tap water, I think I measured it. Last time I measured it was 4. 4.5. Our DI water is 4.5. pH of 8 is what we call basic. pH of 4 is acidic. Now it's a pH of 4. Is there chloride in tap water? Yeah, chloride's a common mineral in tap water, or ion in tap water. So everybody drinks HCl, so it was nothing special. So after that, but it's very dilute. You know, we're talking, the concentrations are extremely small. So it's not like drinking 16 molar. Actually, what's the max on HCl? Is it 16 molar? You know what the max is? About 12 molar. 12 moles of HCl per liter. That's about the max. We can get 16 molar nitric acid. 16 molar nitric is called concentrated nitric. 12 molar HCl is concentrated HCl. Do we use concentrated HCl for everything? No. And so what we're going to do is we're going to do this. Our basic assumptions here, we're going to use what we call standard thermodynamic conditions. Do you guys remember delta H versus delta H naught? Do you remember the difference between delta H and delta H naught? Delta H naught means we're restricting it to standard thermodynamic conditions. So what are standard thermodynamic conditions? Standard thermodynamic conditions, if you forgot, concentrations have to be 1 molar. So if you're 16 molar, that's not standard thermodynamic conditions. Or if you're 0.00001 molar, that's not. Gases have to be at 1 atmosphere or 1 bar. This is an old slide. I should change that to 1 bar now. But in the US, a lot of people still use 1 atmosphere, so it's okay. 1 bar and 1 atmosphere are about the same anyway. Is there a standard thermodynamic temperature? Do you know? 273, 0 degrees Celsius, 273 Kelvin. Is that standard temperature? Yes, for gases, that's what we call STP. But for thermodynamics, is that standard temperature for thermo? No. There's no standard thermodynamic temperature. But the most common temperature that you find the thermodynamic data will be not at 0 degrees Celsius, but at 25 degrees Celsius. 25 degrees Celsius, we call that what? "25 degrees Celsius is called room temperature, even though it's pretty hot, 25. That's standard, that's like 77 Fahrenheit. It's kind of warm. But that would be standard, not standard. There is no standard temperature. That would be the most common temperature that you encounter for our data tables. In other words, room temperature. So we're going to assume that. Now, extremely low or extremely high concentrations may require compensating for. And so our driving forces are just predictions based on standard thermodynamic, that is, these concentrations, these pressures. But if I make it like under standard thermodynamic conditions, I expect to precipitate. So this is my double replacement. HCl plus silver nitrate yields a precipitate of silver chloride and some HNO3. But very dilute concentrations, I might get no reaction. And so it depends. You know, I could drink this stuff, right? This HCl coming out of this tap. I can drink it. Well, it might not react then. And so very dilute concentrations, I take my HCl and I expect to precipitate with silver nitrate. I get no precipitate. Now, to be visible, a precipitate's got to be like a half a milligram or 2 milligrams or something like that. I forgot the exact amount to be able to see by the naked eye. Or if it's very concentrated, like for example, if I use 1 molar nitric acid, it doesn't touch silver chloride. 1 molar nitric acid won't react with HECl. However, if I use concentrated nitric and heat it, so I use hot concentrated nitric acid, then I can get silver chloride to react. And this starts fuming orange clouds. So I didn't write the whole product here. Sometimes adding just a little bit extra here, you know, so I need the stoichiometric amount would be 2 moles of sodium hydroxide. If I add a slight excess of sodium hydroxide, what happens is this precipitate disappears. So I'll form the precipitate and then add a little bit more hydroxide and watch the precipitate disappear, and I form this. This is called a complex ion. This is called trihydroxyplumbate 2 ion. We're going to learn how to name this in chapter 24, but these are common type species. So I have to be careful because sometimes my predictions won't come out accurate if the conditions are quite different here, or if I add excess in this case for this last one. And these are thermodynamic driving forces. When we do chemical reactions and predictions, we want to look at the thermodynamics. So for example, we want to go from higher energy to lower energy. Well, it turns out that diamonds and graphite, they don't have the same energy. When we think of energy, we think of 2 types of energy. You know, if I want to know the energy of graphite, what are the energies I'm thinking of? You guys remember? The total energy is the sum of the blank energy plus the blank energy. The kinetic and potential energy. And so if I look at the total energy of diamond and compare that with the total energy of graphite, are they the same? Well, one thing is, are they at the same temperature? Yes. We're going to make both of these at 298 Kelvin or room temperature. So if I look at room temperature diamond and room temperature graphite, are they the same energy? Well, kinetic energy, they're the same. Because kinetic energy, temperature is a measure of the kinetic energy, so they're both going to have the same average kinetic energy. And so the kinetic energy is the same, however, the potential energy is not the same. Now, when we think about chemical potential energy, what do we think of? We think of bonds and bonding arrangements. So if you recall graphite versus diamond, diamond has what we call an sp3. Do you guys remember sp3, sp2, sp? Yeah. Diamond's sp3, which is tetrahedral carbon atoms in a network covalent lattice. Graphite is sp2, trigonal planar. So this is tetrahedral carbon atoms, this is trigonal planar carbon atoms. These trigonal planar form sheets. It turns out that this trigonal planar arrangement is a little bit more stable. And so we have a thermodynamic driving force. And so going from diamond to graphite is downhill. We should go diamond to graphite. That's downhill, that's a driving force. That's a thermodynamic driving force. And so diamond should decompose into graphite. Basically, there's a driving force for that reaction. However, we don't have to worry about that happening. You don't have to worry about your diamonds decomposing. Why? Because in order for diamond to decompose into graphite, we have to break all those sp3 carbon-carbon sigma bonds in valence bond theory. Or the sigma MOs in MO theory. In MO theory, we've got to break all the bonding MOs, and right, you got to do that. And that's going to cause a lot of energy. So in order to go downhill from diamond to graphite, it first has to climb up a hill. And this climbing up the hill means we got to break all the bonds in diamond and replace those with bonds in graphite, then we're more stable. Well, climbing up that hill, that turns out to be a very steep hill to climb. And it turns out to be too steep. And so what's going to happen is diamond is what we call metastable. It's kinetically stabilized. Kinetics tells us how fast this is going to happen. This is not going to happen very fast because of that hill it's got to climb. And so to properly answer the question about predicting reactions, we need to know the thermodynamics and the kinetics. We can't ignore the kinetics. However, for us, we're going to ignore the kinetics. We're just going to look at the thermodynamics. We're just going to see, is there a thermodynamic driving force or not? Later on, we'll add the kinetics when we get to chapter 20. But we aren't getting to chapter 20 anytime soon. So we're going to look at metathesis reactions first. Metathesis are finding favorable ion combinations. And so in double replacement, what we do is we just swap ions. Do they like the new partners better or the old partners better? That's what we do. But in more complex reactions, we'll just come up with an inventory of ions and see which ions like each other the most. What ions like each other the most? In terms, we want to form thermodynamically more stable products. What types of things are thermodynamically more stable? Precipitates are. Gases, weaker acids. And so we're looking for formation of precipitates, gases, or weaker acids from stronger acids. Okay, these are favorable ion combinations. Sometimes we don't have ions, like this. So if I did silver nitrate plus ammonia, do you see the ions there? Do we do metathesis there? And it turns out this is a metathesis reaction, but ammonia is not an ion. Ammonia is a molecule. However, ammonia is what we call a weak electrolyte, and weak electrolytes partially hydrolyze water. And so ammonia can partially hydrolyze water to form some ions. And so even though this doesn't look like a metathesis reaction, it is a metathesis because what happens is the ammonia hydrolyzes water. Ammonia is a weak base, and it's going to form a little bit of ammonium and a little bit of hydroxide. This is heavily favored in the reverse direction here. But we still form a tiny amount. And these tiny amounts of ions here can react in a metathesis reaction. So we can have weak electrolyte molecular compounds participate in metathesis reactions as well. All right, so let's look at the driving forces one by one. First one is formation of a precipitate. Precipitate's an insoluble solid. And there are a number of different solubility rules. I posted ones from our book. These ones come from Chem 4 here. Some instructors use this, some don't. So I'll give you two that you can use, either the ones from the book, chapter 5, or these. There's 7 of these here. And let's look at number 1. Group 1 and ammonium compounds are all, you heard these? Tristan, do you remember that? The first one here, group 1 and ammonium are all soluble. So, these are all soluble. So if you had ammonium phosphate, soluble. Ammonium chromate, phosphate. Ammonium carbonate, soluble. Sodium is group 1. Lithium, group 1. Potassium, group 1. All those salts combined with any anion should be soluble. Now, these are not solubility laws. These are solubility rules. Laws are held to a more stringent standard, but still not perfect. Rules are held to a much lower standard. And so there are exceptions. There are lots of exceptions to those rules, and most of the exceptions are kind of rare. So, for example, sodium uranyl acetate. Have you ever heard of that? Sodium uranyl acetate is a sodium salt, but it turns out it's insoluble. It forms a precipitate. But it's not that common, so we're not going to worry about it. All right, number 2. Well, once we look at the cation, we look for this cation, and then we switch to anions. And for the remainder of these, we're looking at the anions. And so as far as anions go, the first set of anions we're going to look at are the nitrates. What's the formula for nitrate? Formula for nitrate. This is another thing you want to review. It's easy to forget. Nitrate is NO3, and the charge? Close, but not quite. Not 2 minus, minus 1. Nitrates, acetate. There are 2 ways of writing acetate. Do you know them? What are the 2 ways to write acetate? One way is via the condensed structural formula. So if we take the Lewis structure and condense it, we come up with this. This is called CH3COO minus. Condensed structural formula. The other way is just the formula. C2H3O2 minus. Nitrates, acetates, and chlorates. Remind me what the formula for chlorate is. What's the formula for chlorate? Do you remember all those? You had the chlorate, the perchlorate, the chlorite, the hypochlorite, that series, very common series.
ClO3 minus.
ClO3 minus, okay. So you have the nitrates, acetates, and chlorates are all soluble. It doesn't matter what you attach. Lead 2 nitrate soluble. Chromium 3 acetate soluble. Now again, this is a rule. Mercury 1 acetate soluble, but it turns out mercury 1 acetate is insoluble. But there are exceptions. It's not perfect, but we'll get you started. Okay, after we look at nitrates, acetates, and chlorates, then we're going to move to chlorides, bromides, and iodides. What is the formula for chloride? Cl minus. Bromide? Br minus. And iodide? I minus. Chlorides, bromides, and iodides. What about fluorides? Why are fluorides missing? The reason fluorides are missing is because there are too many exceptions. If you need to know the solubility of the fluoride salt, look it up. And now these are all qualitative. When we say soluble, how soluble is that? Is that infinitely soluble? No, it's not. Well, just the things that are miscible are infinitely soluble. Okay? And so when we're talking about solubility, we have these qualitative, and for this table versus the book's table, it's a little different. The book is 0.01 molar. This table is 0.1 molar. So soluble means it has a solubility greater than 0.1 molar. The solubility is greater than 0.1 molar. Insoluble means it has a solubility less than 0.1 molar. And slightly soluble, SS, means its solubility is about 0.1 molar. Well, 0.1 moles is not a whole lot. And so if you're like 0.11 moles per liter max, that's not very concentrated, but we're going to call it soluble. And the reason is we have to have a cutoff somewhere, and this is the cutoff. Let's see. All right, chlorides, bromides, and iodides are soluble, except there are some exceptions here, and the exceptions are going to be like silver. And so if I have silver ions in chloride, that's going to precipitate. It's going to form silver chloride. Lead 2 ions and mercury 1 ions. And so chlorides, bromides, and iodides are all soluble except when paired with silver, lead, or mercury. It's lead 2 or mercury 1. Mercury 1 is funny because it's Hg2 2+. Okay, number 4, sulfates. What was the formula for sulfate again? Can you look at the periodic table and tell me? You know, when I talk about the two-pronged approach, you know, we try to minimize the amount of memorization we do. And one of the tricks I use to minimize memorization is to look for patterns. Because the more patterns I can remember, the less memorization I need to do. So I can group things into patterns. So when I look at sulfate, I can look at the periodic table, look at its position, and tell what the charge is. You know? I can get the charge easily because I go -4, -3, -2. This is going to be -2. Chlorate is going to be -1. So I have a pattern there. And then I know how many oxygens I have. For example, do you know how many oxygens phosphate has? 4. Sulfate's going to have 4 oxygens. Chlorate screws things up, and so we have 2 patterns there. Chlorate has 3 oxygens and a -1 charge. So it screws things up. There are 2 patterns. But I know those 2 patterns already. So, sorry. Sulfates are soluble, except silver. Silver is borderline. So silver is what we call slightly soluble. It might precipitate, it might not precipitate. It's borderline. Lead 2 likely will precipitate, especially under standard thermodynamic conditions it will precipitate. Mercury will precipitate. Not just mercury 1, but mercury 2 will precipitate as well. Now oddly enough, lead 4 chloride will not precipitate, lead 2 chloride precipitates. So we have to keep track of the charge. So it goes silver, lead, mercury, mercury, and then calcium precipitates, strontium precipitates, and barium precipitates. Magnesium sulfate will not precipitate. So magnesium's left out. But calcium sulfate precipitates, strontium, as well as barium sulfates precipitate. All right, so there are 3 that are mostly soluble, and then there are 3 that are mostly insoluble, so that gives us 7 total. So we look at the cation, and then we look at 3 anions that are mostly soluble, and then 3 anions that are mostly insoluble, starting with 5, hydroxides. Hydroxides are insoluble, except group 1, ammonium, and calcium, strontium, barium. So calcium hydroxide is soluble. It's not very soluble, but it's soluble considering our cutoffs here. Whereas magnesium hydroxide is insoluble. So calcium hydroxide is soluble, magnesium hydroxide is insoluble. So magnesium hydroxide will precipitate, calcium hydroxide is expected not to precipitate, etc. 6, sulfides. What's the formula for sulfides? S, and do you know the charge on sulfide? Can you look at the periodic table and tell me what the charge on sulfide is? No? Do you know the charge on oxide? What's the charge on oxide? -2. What do you think the charge on sulfide is? -2. You're right. It's -2. So we'll call it 2 minus. Sulfides are insoluble, except group 1, ammonium, and group 2. The difference between group 2 and calcium, strontium, and barium are all in group 2, but magnesium's missing. And so what this means is magnesium sulfide is soluble, whereas magnesium hydroxide is insoluble. And so that's the difference here. So it's not calcium, strontium, barium again. And then number 7. Number 7 will be phosphate. Question?
Oh, what is the, in number 5, what is the first insoluble, or soluble except, or no, sorry, insoluble except, it says after that?
Group 1. Group 1 would be,
Oh, GRP1.
yeah, GRP1.
Okay.
Would be lithium, sodium, potassium, rubidium, cesium. All those would be grouped together. All right, the formula for phosphate? PO43 minus. There are 2 ways you can get it. One is you can just outright memorize it, rote memorization, or 2, you can get it from the periodic table. How did you get it, Tristan?
Well, yeah, I memorized the pattern on the periodic table.
You memorized the pattern on the periodic table? Okay. Let's go. Phosphate, carbonate. What's the formula for carbonate?
Is it CO3 minus?
Close. It's CO3. Charge is off. It's CO3 2 minus. That's what it is. We'll look at the pattern. The pattern comes from looking at the observations. You can figure out, once you see the observations, you can figure out the pattern. So phosphates, carbonates, and chromates. Chromates is not a pattern. Chromates is just straight memorization. What's the formula for chromate?
CrO4 minus.
CrO4, not minus.
2 minus.
2 minus. These are insoluble except for group 1 and ammonium. Insoluble except group 1 and ammonium. All right, so those are the solubility rules. We want to start working on trying to memorize those. So we'll get a precipitate on i.e. formation of insoluble solid. Let me pull this down here. We'll go from a stronger acid to weaker acid. I have my students memorize the 7 common strong acids. These are the 7 common strong acids here, starting with HClO4. HClO4 is called perchloric, hydroiodic, hydrobromic, hydrochloric, chloric, sulfuric, nitric. These are the 7 common strong acids. one of the physical properties of strong acids are strong electrolytes. And what do strong electrolytes do in water?
Conduct electricity?
They conduct electricity very well because they dissociate into ions completely. Have you heard that? So, whereas weak electrolytes don't conduct as well because these just weakly ionize in water. That is, they don't really dissociate much in water. Strong acids do. Now, acid strength is based on how much H plus you generate or hydronium you generate. And so all these will generate the max. So if I take 1 mole of acid, it's going to generate 1 mole of H plus, the max. All of these 7 generate the max, 1 molar, let's say. And so what that means is that they're all the same strength because they all generate the max amount of H plus. Even though HClO4 is the strongest, it doesn't generate any more H plus than HNO3. But all these generate a lot more than, let's say, H3PO4. Okay, what the end result is it's called the leveling effect. Have you heard of the leveling effect of the strong acids? The leveling effect of the strong acids just states that all strong acids have the same strength in water. And so these are all equal in strength in water. They're unequal in strength when we look at a gas phase or whatnot. Whereas these are ranked, from strongest weak acid to weakest weak acid down at the bottom. And so typically what people do is they memorize the common strong acids, and then all the other acids they encounter they assume are weak or weaker. Now if we have multiple weak acids, then we are going to use this table to rank them. So if we're going from HF down to H2S, then that's going from stronger acid to weaker acid. And that would be considered driving force. So again, what you want to do is you want to review strong, weak, and non-electrolytes. It's going to be useful. So strong acids are ionized 100%. This is not a strong acid here. This is some other strong electrolyte. But strong electrolytes are ionized 100%, give high conductivity. Weak electrolytes, partially ionized, give low conductivity, and non-electrolytes don't ionize, and so there's no conductivity there. Okay, the third thing we look for in the driving force of metathesis reactions are gas formation. So if I have hydrogen ions combining with carbonate, that makes carbonic acid. Carbonic acid is very unstable. Do you know what carbonic acid decomposes into? If you take hydrogen ions and combine them with carbonate ions, we form carbonic acid. Carbonic acid doesn't live for very long. It automatically decomposes into H2O liquid and CO2 gas. So here's the gas formation part of this. So carbonic acid, unstable, decomposes. Same thing with sulfurous acid, H2SO3. This is unstable. This is going to spontaneously decompose into H2O liquid plus sulfur dioxide gas, SO2 gas. Ammonium ions and hydroxide ions form an unstable combination which decomposes. This is going to decompose into ammonia. Ammonia is very soluble. Ammonia actually hydrogen bonds with water. And so we'll have ammonia, which will be aqueous or gas, and water. And then if you have hydrogen ions combining with sulfide, we'll form H2S. H2S is normally a gas. It's toxic gas. Hydrogen sulfide, rotten egg gas. If you have hydrogen ions and cyanide, we can form HCN, hydrogen cyanide gas, which is also toxic, etc. So there's certain combinations of yield gases. So what we're going to do for the rest of the period is just to try some metathesis reactions out here. And what I'd like you to do is I'd like you to write the complete equation, figure out what the driving force is, then write the ionic equation and the net ionic equation. Do you guys remember writing net ionic equations and that kind of stuff? Yeah. All right, so let's go ahead and try some of these and try to figure out what the driving force is. So the first reaction we're going to look at will be calcium carbonate and sulfuric acid. Okay, what do you expect? This is a little easier than me asking, what are the chemical properties of calcium carbonate? You know, what are all the things calcium carbonate reacts with? Is sulfuric acid one of them? It turns out it is. And so what forms here? The of how you handle H2SO4. Do you guys recall what the strong electrolytes are? The strong electrolytes are, number one, strong acids. Strong acids are strong electrolytes. Number two, strong bases. Strong bases are strong electrolytes. And number three, soluble salts are strong electrolytes. And so what I would like you to do for H2SO4 is, what a lot of people do is when they go to the ionic equation for H2SO4, they break off both hydrogens. But I don't like that. If we look at the structure of sulfuric acid, do both hydrogens break off simultaneously in the same instant of time? No, what happens is water comes along and plucks one of the hydrogens off. So a water molecule comes along and plucks one. But do they coordinate their attack? That is, let's say this water molecule over here and a second water molecule over here, sink it. So 3, 2, 1, take the hydrogen. No, that doesn't happen. It happens one at a time, usually. So let's say this water plucks that hydrogen off. So we end up with 1 H3O plus here, and we end up with this. This, do you recognize what this is called here? This is HSO4 minus. And what do we call, what's the name of HSO4 minus? This is called bisulfate or hydrogen sulfate ion. Most people call it bisulfate ion. So when we look at bisulfate, is bisulfate one of the 7 strong acids? No, bisulfate is what we call a weak acid. Sulfuric acid, this is a strong acid. Now what's the difference? Well, one of the differences is much harder to pluck the hydrogen off a weak acid than it is a strong acid. That has to do with the structure. So when the water molecule comes on to try to take this one, it's going to have a much more difficult time removing this hydrogen. And so when we have a weak acid, the weak acid only weakly ionizes, meaning it barely ionizes, although this is one of the stronger weak acids. And so the second hydrogen does not come off easily. And so when we ionize sulfuric acid in the ionic equation, it breaks up into this. So in the complete equation, it's H2SO4 aqueous. In the ionic equation, it breaks up into H plus and HSO4 minus. H plus I use interchangeably with H3O plus. Writing H3O plus is kind of a hassle sometimes, so I'll write H plus in these types of equations. In other types of equations, I'll use H3O plus exclusively. But for these, you can just ionize it like that. The second hydrogen does not ionize easily, and there are structural reasons for that here, which we can get into. But you know, the more theory you understand, in this case Lewis theory, the less memorization we have to do. And so, but anyway, I'd like you to ionize it like this. I would not like you to ionize it like this. This is assuming both hydrogens can be plucked off easily. No, that's not the case. And so I prefer you not to ionize it like this. Okay. Now whether you use H plus or H3O plus, I don't really care. You can use whatever you're more comfortable with. Okay, this is good, but there's at least one more or two more driving forces. Can you find it? Maybe. You could write it down, and then what's the other driving force we look for? Now, if you say precipitation is your driving force, show me what's precipitating. You know, if you say stronger to weaker acid, I want you to label the stronger acid, I want you to label the weaker acid. If you say gas formation, you know, I want you to tell me what the gas is that you're forming. And so just don't write driving force. Show me what the driving force is specifically. Let's see. Normally in Chem 4 and Chem 1A, precipitation's easy. But when we get to Chem 1B, it becomes more complicated. So you might say we're precipitating out, let's say, calcium sulfate. But you have to look, what are you doing? You're taking a precipitated calcium carbonate. It's not really a precipitate, it's a solid. But we can consider it a precipitate. And so what you have is you have a competition between two precipitates. On the reactant side, calcium carbonate. On the product side, calcium sulfate. Which one is a more stable precipitate? If calcium sulfate's more stable, then it should go forward. If calcium carbonate's more stable, then it should go reverse, and then we expect no reaction. See, so in this case, it's not a simple precipitation. You can't call this a precipitation reaction because we're sacrificing one solid for another. So we call it a solid to solid conversion. If we have a solid to solid conversion, then we got to figure out which solid's more stable. Now, which solid's more stable depends on a different factor. So one thing we could do is we could just look it up. So when we look it up, what tells us, what's an indication that a solid is more stable than another solid? Well, one indication would be melting point. You know, which one has a higher melting point? The one that's harder to melt is more stable, right? Another indication of this is solubility. Solubility is more direct, so let's look at solubility. So let's say I'm forming the precipitate of calcium sulfate. Calcium sulfate is an insoluble solid, and its solubility, the solubility is not written in molar solubility. It could be written in molar solubility, but this is written in grams per 100 milliliters. So we get 0.26 grams of calcium sulfate dihydrate dissolving in 100 milliliters. So remember that, 0.26 grams in 100 milliliters. What are we sacrificing? We're sacrificing calcium carbonate. If we sacrifice calcium carbonate, what's the solubility of calcium carbonate? The solubility of calcium carbonate is 0.013 grams, but this is grams per liter. And so, so we have to normalize it. This is per liter, the other was per 100 milliliters. So I'm going to leave it in terms of liters. So in terms of liters, this would be 0.013 or 13 milligrams per liter. 13 milligrams per liter versus calcium sulfate. Calcium sulfate would be 2.6 grams per liter. And so calcium sulfate is a heck of a lot more soluble. We can dissolve 2.6 grams of calcium sulfate in a liter versus calcium carbonate, we can only dissolve 0.013. So calcium carbonate's more stable. So your argument for precipitation does not work here. Precipitation is not a driving force for this reaction because calcium carbonate's a much better precipitate than calcium sulfate. Do you see that? And so that's a solid to solid. And so this is more complicated. In all the other, like Chem 4, Chem 1A reactions, you're just taking two aqueous solutions. You're not getting rid of one precipitate for another. And then take a look at gas, you know, going from a stronger acid to weaker acid as well as the gas formation.